for graphing energy, like for example, let's say we're talking about maybe throwing a ball. Just as a simple case, let's say you have ground level and you're standing here and you throw a ball. So let's say you have a ball and you're going to throw it upwards. And let's get a mass for that also. Let's say this ball has mass 3 kilograms. And it starts off, let's say, 2 meters off the ground. And let's say we throw it upwards at a speed of, an initial speed of 15 meters per second. Based on that information, what else do you think we'd be able to calculate about the motion of this ball? Like if you saw this sort of set up on a test, what sort of questions do you think the test question might be asking you after this? Here's this situation, figure out what? Yeah, maybe we want to find the maximum height. Or what else might we want to figure out? What's going to happen to it after it reaches its maximum height? Yeah, it's going to fall down. So we might want to figure out something like, well, eventually it's going to reach ground level. Yeah, maybe what's its final velocity at some other location, maybe when it hits the ground. What's its speed when it hits the ground? Or maybe what's its speed at some other location? What's its speed when it reaches, let's say, 4 meters up? Or maybe we want to know how high it's going when it reaches a certain speed. Maybe how fast is it moving when it's 3 meters up. So there may be a wide variety of other things we want to find out. Maybe we want to know any of these. And for any single one of these, you could draw out an energy interaction diagram and set up the conservation of energy equation, treating the situation as described here as initial. So we describe this situation as the initial situation. And then any one of these as final. But if you were using conservation of energy, the idea of initial to final and comparing them, you'd have to set up a separate conservation of energy diagram and a separate equation for each one of these final situations. So the energy interaction diagram approach, the idea of conservation of energy and writing out that equation, delta E total equals 0, is very useful if you were trying to find one of these. But if you're trying to find lots of them, then it's not really as practical because you'd have to solve the equation multiple times. In the cases like this, as if you're looking at several possible end results, or if you want to figure out not just initial and final, but if you want to focus on what happens in between, sometimes a much more useful approach is drawing a graph of energy versus position. So let's try that out. Instead of setting up the equations, let's make a graph of energy versus position. So let's say this graph is a position axis. And since we care here about vertical position, I'm going to call this the y-axis. So the horizontal axis we're going to call y, and it represents the height of the object. And then the vertical axis is going to represent energy, so we'll call that E. And I'm not going to specify a type of energy because we can graph several types of energy on the same axis. Presumably these are going to be measured in meters and joules, so I should label that. Height in meters and energy in joules. And to graph this, let's try setting up a data table. We care here about the height and also what types of energy are going to be involved. As this object moves, what types of energy are changing? Yeah, potential and kinetic, specifically what kind of potential energy? Yeah, we've got gravitational potential energy. We've got kinetic energy. Those are the only types of energy we need to care about here. I'm also going to fill in a column for total energy because we'll want to keep track of that as well. So tracking these quantities. Let's see what we can fill in. What heights do we most care about here? Or is there any height we know something about already? Yeah, 2 meters. And note that this is specifically if we call ground level 0. You can actually choose any height you want to call 0. We could say the height it starts from is height 0, and then ground level would be -2. Or we could say ground level is called 0, and then the height it starts from would be called y equals +2. Or you could even set, let's say you could set the 1 meter mark as height 0. That way the ball would start at y equals +1, and ground level would be y equals -1. You could choose any height you want to call height 0, and then y is just measuring height from that point. But I think it's going to be probably more intuitive here if we use ground level as height 0. So let's label that. Let's call ground level y equals 0. Then the ball's starting height would be y equals +2 meters. And we'll call that y initial. So filling that in, we have one of the y values we care about is 2 meters. And how would we calculate the potential energy of gravity at that location? Yeah, mass times gravity times height. And in this case, we know the mass, 3 kilograms. And what's gravity? What's G here? Yeah, we'll round that off to 10 for now. More realistically, 9.8, but let's round that off to 10. So 3 kilograms times 9 or 10 approximately meters per second squared. And 3 times 10 is 30. And then y is going to be measured in meters. So overall, we're going to get joules, which means to calculate potential energy, we can just take 30 times the y value. So in this context, all of the potential energies are just going to be 30 times the y value. So when the y value is 2 meters, potential energy will be 30 joules. And we can mark that on the graph. Let's say we mark every meter here. And then maybe we mark energy every 10 meters. Or sorry, every 10 joules. So if we call these, let's see, this is 2 meters, 4 meters. And this is 40 joules, 20 joules, 20 joules, 10 joules, 0. Get everything properly to scale here. Okay, so we could put a point on the graph, for instance, at 230. Or sorry, 260. I'm multiplying by 30. In which case I should probably change the scale here. Let's say we make each of these 20 joules. Might need even more. Let's make each of these 30 joules. So if each one of these grid square tick marks represents 30 joules, that's what we got. So at 2 meters, we're going to be at 60 joules. We could put a point on the graph there. Do we know the kinetic energy at that point? How could we calculate kinetic energy here? Yeah, kinetic energy equals half the mass times the velocity squared. And we know the mass, 3 kilograms. We know the velocity, 15. So 3 times 15 squared divided by 2 would be, what is that, 225 squared. Times 3/2. So 337.5 overall. So that is the kinetic energy at this point. And the important thing is at that location, we now have potential energy and kinetic energy. So what can we do with those? Yeah, add those up to get the total energy. Because total energy is just kinetic energy plus potential energy in this case. More generally, it's all the types of energy we care about in the system added together. So add those 397.5 joules. So we now know everything about that one data point. And I'm actually going to need a lot more space here. We scale this to, let's say each one of these is 100 joules. That should do it. So at 2 meters, we have a mark at 60 joules, somewhere around here for potential energy. And we also have a mark at 337.5 joules for kinetic energy. About a third of the way up there. And also 397.5 for kinetic, for total energy. So that'll be higher up, almost at 400. So we've got those data points in terms of, let me label those, kinetic energy, potential energy, and total energy. And let's see if we can get any more data points. That's the only place where we know the speed. But are there any other locations, any other heights that we might care about here? At the top. And can we figure out where the top is going to be? And also the ground. Yeah, let's actually do the ground level first. Let's fill in 0 meters here. 0 meters. So at 0 meters, what's the potential energy going to be? Yeah. 0 meters times 30 is going to be 0 joules. And we don't know how fast it's going yet, but we do know, what do we know about the total energy here? Yeah, total energy should be the same. During this process, while the ball is in flight, it should be experiencing conservation of energy. Because while it's in free fall, what's the only force acting on it? Yeah, exactly. Assuming there's no air resistance. There's definitely no friction because it's not scraping against some other object. As long as we can ignore air resistance, though, what's the only force acting on this? Well, I just say gravity. The gravitational potential energy is one of the energies involved. The force would be the gravitational force, or just force of gravity. That is, as it's moving, or even if it's just staying still, gravity is pulling down on it constantly. But while it's in free fall, that's the only force acting on it. If it was like resting on the ground, gravity is pulling down, but the ground is also pushing it up to balance that out. But while it's in free fall, gravity is the only force acting on it. And gravity is already taken into account by potential energy. So there's no other forces and therefore no work being done. So this is a closed system. That means we can assume total energy does not change. So it's the exact same 397.5 joules the whole time. So this entire E total column is going to be 397.5 joules throughout the entire column, which means what does the kinetic energy have to be here? If we still want potential energy plus kinetic energy to add up to E total, it is going to be at its maximum possible, but what is that value going to be? Yeah, that should equal total energy. Although that's not strictly speaking the mathematical maximum, because we could keep going. We could have, for instance, y could be, let's say, -1 meter. What would it mean physically for y to be -1 meter here? Yeah, it'd end up underground. Because if we're defining y equals 0 to be ground level, then y being a negative value just means you're under the ground level. And that's possible. You can certainly have an object underground. Maybe there's a hole that maybe we're holding it over the hole and throwing it up and it falls into the hole. Or maybe we're on the edge of a cliff or something. So you can certainly have the ball go under y equals 0, in which case, what would be the potential energy? Yeah, we'd have a negative value for potential energy. And that's totally possible. It is fine for potential energy to be a negative value. That just means you are below the location we were defining as 0. In fact, we could just mathematically plug in -1 meter to the equation for y. We get 30 times -1, so that'll be -30. So if the ball reaches -1 meters of height, that is 1 meter underground, it will have a potential energy of -30 joules. E total is still going to be 397.5 joules. So what would kinetic energy have to be to make those add up to 397.5? Yeah, that's going to have to be 427.5. And note that that's more than E total. It is certainly possible for kinetic energy to be more than E total, as long as it's possible for potential energy to be less than 0. That way they still add up to the right amount. So 397.5 isn't really the maximum kinetic energy. Kinetic energy could just keep going higher and higher and higher if the ball is allowed to go underground. Any questions on that so far? So let's see if we can calculate the maximum height. We don't know what that is yet. Let's just label it some unknown Y max, which means we don't know what the potential energy is either. And we don't know what the kinetic energy is. Actually, I guess we do. If it has reached its highest possible height, what speed is it going at that maximum height? Yeah, if it's reached its maximum height, it has to come to a stop because it's getting slower and slower on the way up. At some point, it comes to a stop and then starts to fall back down. So at maximum height, we should expect 0 joules of kinetic energy. You could also think of this as these are sort of oppositely related. As one of them increases, the other one decreases. So to get the highest potential energy, we need the lowest kinetic energy. And kinetic energy cannot be negative because of the squared and the velocity there. So 0 joules is the lowest possible kinetic energy. E total is still the same, 397.5 joules. So at that location, what does potential energy have to equal? Yeah, that's got to equal the total energy, 397.5 joules. So that means we can, now that we know the potential energy at that point, we can calculate Y max by working backwards. Set potential energy equal to 397.5, and then how would we solve for Y? Yeah, divide by 30. 397.5 joules divided by 30. So that would be what, 13 and a bit? 13 and a quarter. So that's going to be the maximum possible height. We can now fill that in, 13.25 meters. And I think now we have enough information to start really graphing this, because we know this is the highest it's going to be. And it occurs to me that I'm really going to need to rescale this graph, because we don't need to go up to just 5 meters. We need to go up to, let's say, 14 or 15 meters. I've got 5 tick marks here. So let's say each tick mark represents 3 meters. So we've got 3, 6, 9, 12, 15. Is it possible for kinetic energy to be negative? If you take a look at the formula for kinetic energy, is there any way that formula could produce a negative result? Yeah, that doesn't work, right? The only ways this could be negative is if mass is negative, which doesn't make sense, or if v squared is negative, which is only possible if v is imaginary, which doesn't make sense. So kinetic energy is never going to be negative. It can be positive, it can be 0 if the object is at rest at that moment. But kinetic energy cannot be negative. You're welcome. Potential energy in this context can, or at least potential energy of gravity can be negative as long as y is negative. And that's fine because y being negative just means the object is below the location we're calling 0. And there's nothing special about y equals 0. That's just whatever we're using as the reference point to measure height from. So y equals 0 might mean ground level, or it might mean sea level, or it might mean the starting height. It's just whatever location we're choosing to measure everything from. Now that we've got all these measurements though, and certainly this is not complete. We haven't listed every possible y value because there's infinitely many, but we've listed many y values, and I think that's enough to establish a pattern. Let's start by putting these in the right spot. These should be all at y equals 2. So that's something more like here. And likewise at 0, we could say at 0, potential energy is 397.5. And kinetic energy is all the way down at 0. Or no, sorry, kinetic energy is not 0. Kinetic energy is all the way up at 397.5. And potential energy is down at 0. And then if we put in a few more data points, we know, for instance, when y is 13.25, potential energy is up at 397.5. And kinetic energy is down at 0. And we could also fill in -1, for instance, if we assume that there's a possibility of the ball falling into a hole. At -1, kinetic energy is 427.5, up above 400. And potential energy is -30, so down here somewhere. Also, what do we know about E total at all of these locations? What's the value of E total? Yeah, it remains constant, right? If E total is constant, what should its graph look like? What is the graph of yeah, it should be a horizontal line, right? E total is 397.5 everywhere. So no matter what y is, E total is always 397.5. So that'll just be a horizontal line. The other ones, what sort of shape do potential energy of gravity graph and kinetic energy graph seem to be making here? Yeah, those seem to be linear, at least based on the data points we plotted so far. Can we confirm why that would be? Like, mathematically, can you explain why the potential energy of gravity graph should be expected to be a straight line? What is it about potential energy of gravity that suggests it should be a straight line? What was our formula for, how are we calculating all these potential energy of gravity values in the first place? Where did we get those values? Like, how do we calculate the 60, the 0, the -30? Yeah, those are from mgy. That is, in this context, 30 times y. So we've got output equals 30 times input. That is a constant times input. If you just graph output equals a constant times input, what shape does that always form? If we're just graphing some function of y equals a constant times y, yeah, that's always going to form a line. And moreover, it's a straight line through the origin because we don't have plus a constant. But in general, anytime you're graphing output equals constant times input, that's always going to be a straight line through the origin. If it also has plus a constant, then it won't go through the origin anymore. But in this case, it does. And what does the 30 tell you about that line? What does that constant multiplier tell you about the shape of the line? Exactly, that's the slope. So potential energy of gravity will be a straight line with slope 30 through the origin. So that is our graph. And that can keep going, at least theoretically. The object doesn't keep moving past 13.25 meters up, because that is the maximum height. But mathematically, we can have the potential energy of gravity graph keep going as long as we want. What we usually do is draw it as a dotted line after that point, because we know the object isn't going to get any higher than 13.25. So what we often do is just draw it as a dotted line beyond that point to say it's not going to go past this point, but the graph itself mathematically can keep going. What about the kinetic energy graph? Why would we expect that to be a line? Can we justify that mathematically? Because the thing is, based solely on the formula, half the mass times speed squared, if you're graphing something equals something times input squared, what shape would you usually expect that to be? Yeah, if it's got something squared in it, the variable squared, we would usually expect it to be a parabola. But these points are very definitely not forming a parabola. They are forming a straight line. And I'm a little off there. Maybe I should adjust those values, because these really should form a straight line. But why is that? Why are these not forming a parabola? Why are they creating a straight line instead? The thing is, I would expect this to create a parabola if you were graphing what axes? Kinetic energy is a quadratic function in terms of what variable? What variable is actually being squared there? Yeah, the velocity is what's being squared. So if we graphed kinetic energy versus speed on a graph, like if speed were the other axis, then that would be a parabola. But that's not what we're doing. The horizontal axis here is not speed. What is the horizontal axis? Yeah, it's height in meters. And kinetic energy is not equal to height squared. So when we're graphing kinetic energy versus height, this formula doesn't even matter. Kinetic energy is not proportional to height squared, it's proportional to speed squared, but speed does not play a factor in this graph. So what we would need instead is some formula relating kinetic energy to height. And we can't do that directly because kinetic energy does not depend on height. But one thing we can do, kinetic energy is related to potential energy based on what facts? What's the relationship between KE and PE in this graph, or in this situation? What do they have to add up to? Yeah, they've got to add up to total energy, and total energy is constant. So we know that potential energy plus kinetic energy equals a constant. And potential energy is a function of height. Let's write that as potential energy of y, because it is a function. If you solve this for kinetic energy, how would you isolate kinetic energy in this equation, the conservation of energy equation? Yeah, subtract potential energy from both sides. So kinetic energy is negative potential energy plus a constant. And now we're getting somewhere because we can use some facts from algebra here. Potential energy of y is a function of y, so it creates this shape on the graph, this diagonal line. But we're taking, to find kinetic energy, we're taking negative potential energy of y. What happens to a graph if you take the opposite, the negative of the function? Well, in this case, the slope becomes negative because it was already positive. But in general, for any graph, whether it has a defined slope or not, if you just take some function and apply a negative sign to it, geometrically, what does that do to the graph? Like, for instance, if you graph y equals x squared and then you graph y equals negative x squared, how does that change the graph? In this case, yes, it will make the line decreasing. But more generally, what does a negative sign do to any graph of any function? For example, if you were to graph y equals x squared, you'd get a parabola shape. What if you instead graphed y equals negative x squared? how would that graph be different? Yeah, it's going to be a parabola that opens downwards. Exact same shape, but flipped across the y-axis. Yeah, exact opposite orientation. That's generally what a negative on a function does. If you have a function and you know its graph, whatever shape that function is, if you apply a negative sign to the function algebraically, then geometrically it just takes the graph and flips it upside down. Specifically, it reflects it across the y-axis. So all that negative multiplier is going to do, that negative multiplier takes the graph we've already got and reflects it precisely across the axis. So potential energy graph is this line with a positive slope. The negative of potential energy is the exact same line, but flipped across the axis. But we also have plus a constant. What does plus a constant do to a graph? If you have a graph of some function and then you just add, like let's say you just add 5 to the function, what does that do to the graph? Yeah, that's going to shift it up or down. And since we're specifically adding 397.5, and by the way, I wouldn't necessarily call it the y-axis, because in this case, the y-axis is the horizontal axis and the energy axis is the vertical axis. So in this case, I'd say it moves it up on the energy axis. But that plus a constant, specifically we're adding E total, which was 397.5. So that's just going to take this graph and shift it up 397.5, locking into place there. And that's our kinetic energy graph. So this is really where the kinetic energy graph comes from here. The kinetic energy is equal to opposite of potential energy plus a constant. The opposite sign takes the shape and flips it across the axis. Then plus E total shifts it up on the energy axis, or possibly down if E total happens to be a negative value. But that creates the kinetic energy graph. So in general, the kinetic energy graph is going to be essentially a mirror image of the potential energy graph, if those are the only types of energy involved here. If you only have 2 types of energy involved, let's say potential energy and kinetic energy, the kinetic energy graph will be a mirror image of the potential energy graph. You can also look at this conceptually in the sense that as potential energy increases, kinetic energy has to decrease at the same rate. So their graphs are going to be mirror images of each other in that sense. Opposite changes. Any questions on that so far? And one of the useful results of this is we can now use this graph. Note that this graph doesn't just show some initial value and some final value. This graph shows all the in-between values. So we can use this graph if we want to answer some of these other questions. For instance, what's the maximum height? We found that as the location where kinetic energy is 0 and potential energy reaches its maximum, 13.25. Or if we wanted to know, for example, what's its speed when it hits the ground? Where on the graph should we look if we want to know the speed when it hits the ground? Yeah, if we just take a look at y equals 0, and then trace up from there, we can identify what's the kinetic energy at that location, and then set that kinetic energy equal to half the mass times speed squared and solve for speed. Or if we wanted to know something like, what's the speed when it reaches 4 meters up? We can just take a look at 4 meters, identify what's the kinetic energy there, and then again, set that equal to mass over 2 times speed squared and solve for speed. So you can use the in-between points on the graph to figure out information about any of those intermediate locations. Any questions on that graph? Yeah, you're welcome. And for extra practice on this, I would recommend trying setting up another example on your own using spring potential energy instead of gravitational potential energy. Let's say you've got a spring attached to a wall. You've got an object on the end of the spring with some mass. Let's say you know the mass, you know the spring constant, just pick some numbers for those. Let's say you pull the spring back to a certain point and let go, let it oscillate. Try drawing out the spring potential energy and the kinetic energy as a graph. And I would recommend assume it's a horizontal spring, so you don't have to worry about potential energy of gravity. But try drawing out a data table with some sample locations and a graph as a scatter plot, and then fill in the curves for spring potential energy and kinetic energy and E total. So that'll get you some more practice and also develop some intuition of how springs work compared to how gravity works. So give that a try, and I will see you next time. You're welcome.